Everybody, this is Teacher Yong Lam, and welcome to the Common Mistakes explanation for our first ever HAL Math mock test. Right, so we have received a lot of submissions from y'all, and here's a analysis of the accuracy rate for each of the problems. Right, we can see that most of the questions, right, at least 50% of you got it correct, but there are some questions, mainly those that I have labeled in red, that perhaps need some explanation from me. Right, so this video is here to guide you through some of these more challenging questions, and it serves as a reminder for some of the key knowledge points, right? Some key concepts as a revision of them. Okay, so without further ado, let's get started, right? Let me delete this picture and let's look at the 7 questions today. All right, so first, let's take a look at question 5. It is asking which of the following has exactly 2 lines of symmetry. Right, so what exactly does lines of symmetry mean? So you can imagine you have a shape. For example, I have a heart shape. Right, a heart shape, right? Maybe this is not that symmetrical, right? We say that a heart shape is symmetrical because I can find a line that when I cut it through, and I fold the 2 parts together, right? Like what I'm doing to my hands now, right? Then you will notice that the 2 sides have the exact same shape, right? They look exactly the same. So this line is what we call a line of symmetry. Sometimes a figure can have more than one line of symmetry, right? A very classic example will be a rectangle, right? A rectangle can have a horizontal and a vertical line of symmetry that causes it to have 2 lines of symmetry, right? So we need to look at each of the figures, right, to check out, right, where is the line of symmetry. Okay, so all of these figures are basically squares, right, with colored tiles inside. Now, if we look at a square, there are some common lines of symmetry, mainly a vertical line of symmetry, a horizontal line of symmetry, and also the diagonals are also lines of symmetries. Right, so these are some of the common lines that we will check to see if the shape is symmetrical when we cut that line. Okay, so let's take a look at figure A. Right, figure A, you want to see when you cut the line, both sides, do they look exactly the same? Okay, so for example, if I cut it vertically, the left and the right, they are mirror reflections of each other. They look exactly the same. So yeah, that is one line of symmetry. Likewise, the horizontal one is also a line of symmetry, right? In fact, if you rotate it, it looks the same, right? So since I have found 2 lines of symmetry, does that mean this is the answer, right? Not necessarily, because I need to have exactly 2. But in figure A, you notice that if I draw a diagonal along this direction, right, then you realize whatever happens on one side and whatever happens on the other side, they are also exactly mirror images of each other. That means, right, this diagonal line over here is also a line of symmetry. Likewise, the other direction's diagonal is also a line of symmetry, right? They look exactly the same, right? The both sides. So figure A has 4 lines of symmetry. For figure B, you will notice that, hey, even though I can still cut in the middle, but on the left and on the right, it is different, right? Here it's shaded, here it's unshaded, right? They don't look the same. So in that case, this vertical line is not a line of symmetry. Likewise, the horizontal line is not a line of symmetry. Likewise, the diagonal is not, right? You see one side unshaded, one side shaded. So that is not the case. So B has 0 lines of symmetry. C, however, you see the vertical line in the center, right? When I cut through it, on the left side and on the right side, it is not mirror images of each other, right? You can just look at the middle 2 squares. So this means that this is not a line of symmetry, right? The vertical line is not a line of symmetry, but the horizontal line is also not. However, you can look at the 2 diagonals, right? For example, if I draw this diagonal, you'll realize that, hey, this and this, right? They are forming mirror images of each other. Similarly, this is also forming mirror images of each other through this line, right? So you see whatever happens on this side and whatever happens on this side later when the thing goes away, right? You realize, hey, they are exactly mirror images of each other, right? For example, you can just take the corner that I've drawn. So there are 2 lines of symmetry in C, right? So my answer is C. For D, there is only one line of symmetry, right? Which is the vertical line of symmetry. So we choose C as our answer for question 5. The key point here is what actually defines a line of symmetry. You want both sides to be mirror images of each other that look exactly the same. Right, so that will be question 5 for symmetry. Moving on to the next question, right? We are looking at addition and multiplication principles. Honestly, I have gone through a lot of such questions, right? If you see this in HAL, right, it's actually pretty time constrained, right? According to previous tests, it's 75 minutes for 50 questions. That's a lot, okay? But so sometimes we need some more efficient tools such as addition and multiplication principles. But if you want to list, go ahead. So how do we do this using addition and multiplication principles? The question is asking how many four-digit whole numbers have four different even digits and a ones digit greater than its thousands digit, right? So we have a four-digit number. We want the ones digit to be greater than the thousands digit. So the only relationship, right, involving who is big, who is small, is that the thousands must be smaller and the ones must be greater. And also, we know that this four-digit whole number we want to form will have four different even digits. That means we are choosing four out of the five digits I've listed over here. 2, 4, 6, 8. And don't forget 0. Now, of course, 0 cannot be at the highest place, so you need to take note of that. So we need to choose four of these digits to put into the four-digit whole number so that the ones digit is greater than the thousands digit. How can we do that? Right, we can think in terms of cases. Let's say I put 2 as the thousands digit. Now, 2 has to be smaller, right? The thousands digit is smaller. So we need to choose a greater ones digit. That means maybe I can put 4 here, right? 2 and 4, right? 2 as the thousands, 4 as the ones. For the remaining two digits in the middle, as long as they are even, as long as they don't repeat, I'm actually fine, right? I can arrange them however I want. So maybe I can put 2, 0, 6, 4, 0, 8, 4, right? 2, 6, 0, 4, 2, 6, 8, 4, 2, 8, 0, 4, 2, 8, 6, 4, right? I can try to list out the number of ways, right? Or rather, all the ways to choose the middle two digits. And you can see that, right? I can have 6 ways to arrange the middle two digits after fixing 2 as thousands, 4 as the ones. All right. So this is one way to choose the thousands and ones digits. However, if I choose 2 as the thousands digit, I can also choose a greater, even greater ones digit, that is 6, right, to be the ones digit. And similarly, the digits left are 0, 4, and 8, right, which I can arrange in the middle two positions in how many ways? Let's try to list them out, right? List in order, right, without any repetition. 0, 4, 0, 8, then we move on to 4, 0, 4, 8, right? 8, 0, 8, 4. And you realize there will be another 6 ways. So actually, you will realize that after I have selected my thousands and my ones digit, there is always 6 ways to form the exact 4-digit whole number given the thousands and the ones. Right? So if I have 2 something something 6, that will be 6 ways as well. So what is left is try to find out how many ways we can choose the thousands and the ones digit. Right, so just now we have 2 something something something, right? We did 2 something something 4, 2 something something 6. We can also choose 2 something something 8, and that gives me another 6 ways. Right, but that doesn't mean your thousands digit has to be 2. It could be 4, right? 4 something something 6, right? Ones has to be greater. 4 something something 8, right? Each of them will contribute another 6 ways, right? These 6 ways comes from the arrangement of the middle digits. And then if you choose 6 as your thousands, you can do 6 something something something, right? And the ones digit has to be greater, it has to be 8. That gives me 6 ways. Now, if I choose 8 as my thousands digit, then my ones actually cannot be any bigger than that, right? Because 8 is already the largest we have. So I don't need to consider this case. So as you can see, we have 1, 2, 3, 4, 5, 6. 6 times 6 ways, right? This is where your multiplication principle comes in. There are a total of 6 times 6 equals to 36 ways to form these 4-digit whole numbers. Okay, so this is how you can do that with some listing and some addition and multiplication principles application. All right, so hopefully when you see this in a future paper, you know how to do it, right? Now, let's come to question 25. Now, honestly, this question has caused a lot of heated discussions, right? Because to be honest, the question is not that clear, right? We don't exactly know how cutting open a link works. But it's okay, let's read the question first. Right? A man has five separate chains as shown below, right? Each consisting of three links. He wants to connect them into one chain of 15 links. That means he needs to break open some of the links. Okay, and then he needs to, you know, put these links together. Now, a blacksmith charges 50 cents to open a link, to cut open a link, right? $1 to weld a link closed, and none for bending links. What is the minimum cost to make the 15 link chain? Okay, so over here, the question may not be that clear. Perhaps it's due to a translation error or whatever, right? But actually, let me just show you two scenarios, right? And how to solve the question in each scenario. And it all lies in the definition of cut open one link. Okay, so actually, there are two ways to understand this, right? Let's say, number one way, cut open one link means I break open a little oval, I cut it up, right? I make it into a C. So for example, this little O, I cut it up, I make it a C, right? So in that case, how do we do that? Actually, all I need to do is to focus on one of the chains, right? It has three links. Then I will cut open all these three links, right? Meaning from O, I make them into C, C, C. So I actually did three cuts, right? These three cuts, that will cost me 50 cents times three, which is equal to $1.50. All right. Then I am going to use the first C to connect the second and the third. And I'm going to weld the link close, meaning I'll turn it back into an O. Then the second C, I will use it on these two. The third C, I will use it on these two. And then you realize you have now a full long chain. And that is actually three welding, in other words, three connections, which will be $1 times 3 equals to $3. That will give me a total of $1.50 for the cutting plus $3 for the welding or connecting, and your minimum cost needed is $4.50. Okay, now this is what happens if we literally treat cutting one link as making one O into a C. All right, so actually, this is what perhaps gets the closest to the understanding, or rather the interpretation that the question wants you to have, right? Now, the second interpretation that some of you might have is instead of cutting open, referring to cutting open one link, maybe you might think it means I want to cut a chain, right? In other words, I'm cutting off one chain. Like this is cutting a chain. So in that case, this is sort of related to interval problems, right? We want to connect all these five mini chains together. What I can do is first I will cut the middle three. Right, I want to make as few cuts as possible. I don't need to cut open everyone. I just need to connect the middles to the sides. So I will cut open the middle, and then maybe it will become something like OC and CO. Right, OC and CO. OC and CO. Right. Then later I will use it to connect, 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 connect. Right. So then that is how we can do this. Okay. So when we cut a chain, 1, 2, 3. That will be 3 times, right? So I cut 3 cuts. Similarly as just now, that will be 50 cents times 3 equals to $1.50. But this time, the merging, right, is 4 times of merging or 4 times of welding. Each time of welding is $1. So $1 times 4 is equal to $4. And the total cost will be $1.50 plus $4 equals to $5.50. So if cutting open a chain, right, that means you cut once on a chain, it takes 50 cents. This is the least that you can take, right, to make the whole chain connected. Now, of course, this question is not really that clear what it means. But if we take it literally, right, cut open a link and each link is actually one O in a chain, then perhaps the first way is the correct way to go, right? So the answer is actually A. Okay, that's why some of you might be a bit confused, right? And that's why the accuracy for this is particularly low. But no worries, right? Depending on the interpretation, you can solve this question differently. For me, I will take the first interpretation. All right. Okay. Now with that, let's move on to a lighter question, right? Previously, that one could have burned your brain a lot, right? But this question is actually not that difficult. Follow the pattern. What is the 10th number, right? The one in the blank, counting from the left to right. Now, you might notice that the sequence is increasing by a lot, right? Wow, the numbers keep on increasing by a lot. Now, if you notice that the increases start off small, but they get bigger, bigger, right? At the end, maybe you might want to check, right? What's the difference? What's the product? Okay. So for example, difference means we take 1 and 3 plus 2, right? Plus 2, plus 2, plus 9, plus 15, right? And then you realize there isn't particularly any pattern. So maybe instead of thinking of it as an addition relationship, right? Addition to cause the increase, maybe the increase is caused by a multiplication pattern, right? So let's see, from 1 to 3, maybe it's a times 3. From 3 to 5, you don't multiply by a whole number. So unfortunately, it doesn't work as well. But here, this is where I want to introduce a specific special type of pattern called a Fibonacci pattern. Right. What is a Fibonacci pattern? A Fibonacci pattern is a pattern that is formed by taking some previous terms, summing them up to get the next term. So for example, a classic one will be starting from 1 and another one. And the next one will be 1 plus 1 equals to 2. The next one will be 1 plus 2 equals to 3. The next one will be 2 plus 3 equals to 5, so on and so forth. Right? I'm taking the previous two terms, add together to get the next term. All right, so that is how a Fibonacci pattern works. Now you might think, teacher Yong Lam, 1 plus 3 is not equal to 5. Well, true, but you don't have to add two numbers to get the next number, right? In fact, this question is very sneaky because you actually need to add four numbers to get the next term, right? If you don't believe me, let's look at the first four terms, right? 1 plus 3 plus 5 plus 7 is equal to 16. You get the fifth number. Then let's try one more round, right? 3 plus 5 plus 7 plus 16, everything here, that will be equal to 31. Right, and then 5 plus 7 plus 16 plus 31, that will be equal to 59. Oh God. So if you keep continuing the pattern, you will realize to get this number over here, you will need to take the previous four numbers added up together. That will be 31 plus 59 plus 113 plus 219. All right, now let's perform the addition. 31 plus 59 is 90. 113 plus 219 is 332. Right, so then you will get 422 as the missing number here. All right, now of course, you want to check your answer to see if the pattern really works. So what you can do is you can take the next four numbers here, 59, 113, 219, and 422. Add them up and see, will they give you the number 813? If they do, that means your answer is correct. The pattern that you figured out is correct as well. Okay, now with that, that is question 30, a lighter one. Okay, now let's move on to question 36. Okay, question 36 is an interval problem, right? And it's not the usual interval problem in a line, right? Let's read the question. There is a big square-shaped cake. The length of each side of the cake is 30 cm, right? Each side is 30 cm. So let's maybe label, right? Each side is 30 cm. There are strawberries placed along the sides 6 cm apart from each other. There is also a strawberry at each corner of the square. How many strawberries are there on the cake? Right, so let's take a look at what happens according to the question. You realize that we have a strawberry at each corner of the square cake. And then I am going to put more strawberries along the sides, and each strawberry is 6 cm away from the previous strawberry. Right, so something like this. And it happens on all four sides. Now, perhaps looking at an entire shape is a bit complicated. It's too much. It's okay. Let's focus on the line. Right, let's focus on one row. If we focus on one row, you will realize that the total length of the row is 30 centimeters, but each interval or each gap between two strawberries is 6 centimeters. So in that case, 6 centimeters, 6 centimeters, 6 centimeters. How many 6 centimeters does it take to complete a 30 centimeter side? That will be 30 divided by 6 equals to 5. That means I split the total 30 cm into 5 6 centimeter gaps, right? So there are 5 gaps or 5 intervals. Okay, now if there are 5 intervals along the row, take note that each end of the row will have a strawberry, right? The left end and the right end both have strawberries. So altogether, there are how many strawberries? There are 5 plus 1 equals to 6 strawberries in total. There are 6 strawberries in total in one row. Meaning, right, one row has 6 strawberries. The other row over here will also have 6 strawberries, right? If we look at the vertical row, there will be 6 strawberries here. If I look at this vertical row, there will also be 6 strawberries. If I look at this vertical row, there will also be 6 strawberries because every side is the same, is 30 cm. Every gap is the same, right? It's always 6 cm apart from each other. So the result will always be the same. Every side will have 5 intervals, 6 strawberries. Does that mean the total will be 6 times 4 equals to 24 strawberries? That seems like a very natural calculation. Until you notice when teacher Yong Lam circled out the rows for you. For example, if I circle this row and this vertical side, you realize that there is an overlap at the corner. This strawberry has been double counted both in this row and this side, right? I have counted this strawberry 2 times. I have double counted this strawberry at the corner. Similarly, the strawberry here, here, and here are double counted since they are the overlap of 2 rows. I have counted them twice. So I cannot say I put 2 strawberries here. Like. If I counted twice, I need to remove the overlap, remove the double counting. I have double counted 4 strawberries. So at the end, I will need to minus 4 to get the exact total number of strawberries, which is 20 strawberries. So you will get your answer 20. All right. Alternatively, you can also think of it as a closed loop interval problem. Closed loop means your objects are not arranged in a row, it is arranged in a circle, right? It is arranged in a circle or in a square or in any closed shape. It's around a shape. In that case, your number of objects is equal to the number of intervals. And you already found out, right? One row has 5 intervals, or one side has 5 6 cm intervals. So there are 5 here, 5 here, 5 here, 5 here. In total, there are 5 times 4 equals to 20 intervals. And that will also imply that there are 20 strawberries. All right, so that will be another way to get your answer if you know how closed loop interval problems work. Okay, so that is Question 36. Let's move on to another question, right? Question 42, rate word problems. Now, this one is slightly tricky, right? Five cats. Let's read the question. Five cats can catch five mice in 5 days. If each cat catches mice in the same rate, how many cats are needed to catch 20 mice in 20 days? So many of you will think, haha, my answer is 20, right? 5, 5, 5, 20, 20, 20. Makes sense. Okay. However, let's think about it in more detail, right? Here we have cats catching mice. Cats are doing the work, right? Our worker here is our five cats. And they are doing some work for a specific period of time. The time taken is 5 days. After they do the work, they get an outcome. In other words, they get a result, right? Outcome or result. They caught five mice in 5 days. Now imagine these five cats are catching five mice in 5 days, and they continue in the same rate. So let's say I give them another 5 days. For the next 5 days, since they follow the same rate, they would have caught another five mice. Likewise, another 5 days. Likewise, that will be another five mice. Then I give it another 5 days. Then they will catch another five mice. And what do you notice? You notice that I gave them a total of 4 times 5 equals 20 days. And the outcome that they get in total is 4 times 5 equals to 20 mice. Did I change the number of cats though? No, the same five cats used 20 days to catch 20 mice, right? So the answer is not 20, the answer is 5, right? You just need to think, what if I have the same group of people? I prolong, I make the time that they do the work longer. How does that change the outcome, right? In fact, in a rate word problem, the key point is whenever you manipulate one of the time or the worker, the outcome will change accordingly, right? So let's say I double the time taken without changing the workers, then of course, right, if I have the same worker, I give double the time, the outcome will also be double. Similarly, let's say I didn't change the time, right? The time is still 5 days. If I double the amount of workers, right, I have more cats, of course, they will catch more mice. In fact, they will also double the mice that they catch. All right, so it's better to write all of the things up. The change in one of these things, right, either worker or time, one change of it will definitely affect the outcome accordingly. In particular, you realize that the goal is asking how many cats will catch 20 mice in 20 days. I try to manipulate time first, right? From 5 to 20, you realize that it is 4 times, right? Fourfold. Now, if I give more time for the cats, right, without changing the cats before I even think about the number of cats, by just multiplying 4 to the number of days, the outcome will also be multiplied by 4, right? Of course, the more time you take, the more the outcome. So, and you get it, right? 20 days, 20 mice. And notice that I didn't even change the number of workers, right? So, in that case, actually the workers is still 5, right? 5 cats will still catch 20 mice in 20 days. I only still need 5 cats, right? And that's it for question number 42, right? A tricky one because the numbers are intentionally set for you to fall into the trap. Okay, finally, let's take a look at question 48, right? Working backwards. Now, let's try to do this with a visual technique, right? There were some pears in a crate. Jovi took out 4 fewer than half of the pears from the crate. Then she divided the remaining pears equally to her 3 brothers. If each brother received 6 pears, how many pears were in the crate at first? So let's show the initial quantity using a bar model, and then we will try to give away the pairs, right, and see how they are distributed. Right, so let's assume this entire bar is representing the total number of pairs at first. Now, Jovi took out 4 fewer than half of the pairs from the crate, right, which means did she actually take half? Right, let's say what actually happens when I didn't say 4 fewer than, right? Let's say I only say half of the pairs. Then what part did Jovi take out, right? This is the entire pairs in the crate. Then I will cut it into half, right? Jovi would have taken this entire half. However, this time Jovi is taking 4 fewer than half. That means, did she actually take away this entire half? No, she took away 4 fewer than that. That means among this half, 4 of it wasn't taken away. So this is the part that was taken away at first. Okay, so now she took this part from the crate and she wants to divide the remaining pairs equally to her 3 brothers. Right, where is the remaining pairs? Can I just say the remaining is this part? No, the remaining also includes the extra 4, right, that is previously not taken. So this part that I have outlined represents the remaining, right? So let's draw a new bar to show the remaining, because later I'm going to use the remaining to do something else, right? So let's say this bar represents the remaining pairs. She divided the remaining pairs equally to her 3 brothers, meaning, right, I split this equally into 3 units or 3 parts, and we know each brother received 6 pairs. So I split the remaining into 3 equal shares. Each share has a 6, a 6, a 6. That means the remaining number of pairs will be 6 times 3 equals to 18. All right. So looking back, if we know that this remaining part is 18 and I have 4 over here, that means this part will be equal to 18 minus 4 equals 14. And take note, what is special about this 14? Just now, we realized that this 14 is exactly 1/2 of the pairs at the start. Right, at the start, I have this many pairs, half of it is mentioned here. So if 1/2 is 14, that means the total number of pairs at first will be 14 times 2 equals 28. And that's why I will have 28 pairs in the crate at first. All right, so this is how we do this question using a bar model. Of course, if you know how to do it with a train diagram, go ahead. Right, I'm just thinking using a bar model to visualize things will make it easier to understand how it works as well. Right, so with that, that is the last question that I will talk to you about today, right, from our first HAL math mock test. The second test has already been released, but do try that out, and I hope to see more improvement from every one of you. Thank you so much, and I will see you when I see you again. Bye bye.